is about work that I've done over a few years, but then haven't looked at in a few years since then. But I wanted to talk about it because it actually has to do with the program's title of Emerging Technologies, which I think, I sort of wanted to push more of the emerging technology aspect to this talk. Okay, and this is joint work with a lot of great collaborators, two of whom are here, one of whom you just heard from. Okay, so this talk is about how to implement data structures in persistent memory. So I'll start by giving you like a really quick crash course on persistent memory. So generally speaking in this talk, I'll discuss NVRAM, which is one type of persistent memory. It's actually now not supported by Intel anymore. However, there are other types of memory that you could, other technologies that could replace NVRAM in terms of its persistence with slightly different assumptions. So I can mention that a little bit at the end. But for now, let's work with the NVRAM model. So what is NVRAM? This here is a computer. And let's think of like, what does its memory look like? Okay, so a computer has some processing units. That CPU uses its cache. The cache is sort of the fastest way to access memory, but it's small. After cache is your main memory, which is usually DRAM. And after that, if you have things that don't fit in your main memory, you have your disk. And there's a lot of technologies for how disk is implemented, but in this talk, it won't actually matter. Okay, and let's look at what happens when a computer crashes. Okay, so if your computer just crashes now, what happens? Well, the CPU obviously stops working, and you lose everything that was in your cache and your DRAM. Okay, but anything that you put on disk remains, and we all know that when we turn off our computers and we turn them back on, most of our things, except for the things that we didn't save, are still there. And you can think of whatever you didn't save as being in main memory and not in disk. Okay, so that's sort of the normal memory model that we kind of have in our minds. And the only difference is that if you replace DRAM with NVRAM, is that now main memory will also remain. Okay, so if your computer crashes and you have NVRAM instead of DRAM, nothing gets lost in main memory. You will still lose your cache though. Okay, so that's sort of like NVRAM 101. This is the persistence we're working with. So instead of just having disk persisted, you have your main memory persistent too. Okay, so that's kind of really nice. You know, you can save more things, but it does raise a few issues. So let's talk about that. So we know that we can't predict when the system will crash. So now let's imagine that I replace my DRAM with NVRAM, and I'm running some operation that I had on my normal DRAM machine, and I didn't think twice about changing it for NVRAM. Okay, and my operations wanted to update 3 memory locations. Okay, and let's say that you weren't allowed to sort of see the memory when only part of that is done. So I want that to be sort of atomic or inside a lock or something. Okay, so it could be the case that I go through and I update 2 of them, and then my system crashes. Okay, so my system crashes, I now wake up and I find that I have 2 updates and not 3 in my memory, right? If I had just DRAM, I would have 0 of these updates, so it would be fine. It would be like, okay, I never started this operation, but here I could kind of find myself in this intermediate state, and possibly the process that started executing this operation is no longer there, nobody knows how to complete it, right? So I could find myself in this inconsistent state just because operations could sort of crash in the middle, but still leave their traces there. Okay. Another issue is that actually this is not how things work, right? We always have our cache. We always write in cache first, right? And so imagine that I have this 3 memory modification operation. What I would actually do is I would make those modifications in cache first, right? And then those modifications would sort of move onto main memory without my knowledge, right? At some point, the cache would evict these, and they would go to memory. So it's quite possible, for example, that my second modification would go to main memory, but my first one and my third one haven't yet. I could, at this point, crash. Anything I kept in cache would be gone. But now, not only do I have sort of a operation in the middle kind of state, I also have out-of-order evictions from cache that leave me in this sort of mixed state where it's like not just in the middle, but like part of it is done, the earlier part wasn't done. I'm very confused. Okay, so these are the kinds of issues that we have to deal with. If we have NVRAM, we want our memory to be in a consistent state when we wake up from a crash. We need to sort of actively think about that. Okay. Okay, and so I'm going to show you a very quick sort of solution for the first problem of, I could find myself in the middle of some operation and I wouldn't know how to continue it, which is we can look at lock-free algorithms. Okay, so lock-free algorithms are a very well-studied class of algorithms. Guy discussed them, Eric discussed them. They've been discussed sort of in this workshop quite a bit. The idea is that we have several processes, but a slow process is not allowed to block any of the other processes. Okay, meaning that, let's say I have some operation on some tree, and P1 has this for modification operation in a lock-free algorithm. Okay, so P1 wants to modify, say, these 4 locations, and it goes through, modifies 2 of them, and now stops for whatever reason. It gets swapped out by the operating system. At this point, if my algorithm is lock-free, any other process is allowed to come into the system and just start their own operation. And so any state in the middle of an operation is consistent, meaning that we know how to continue with the rest of the system from that point. Okay, so we had these 2 NVRAM challenges, which is the first one being if we stop in the middle of an operation, we might not know how to continue it. That's sort of taken care of by just, if you design your algorithms to be lock-free, finding yourself in a state in the middle of an operation is fine, right? However, lock freedom still assumes that memory modifications happen in the order that you tell them to happen, okay? And that's something that lock freedom, if you have out-of-order evictions and you find your memory in a state where the later operations have persisted and the earlier ones haven't, you'd be very confused. You can't deal with that with just lock freedom, right? So we're left with handling these out-of-order evictions, and that's sort of what I'll be discussing for the rest of the talk. How do you handle these evictions? Yeah?
So if I have a write-through cache, does that mean that this is not a problem, essentially, that at this point it's solved? Is that...
Yeah. So there are other problems that remain. For example, there's always like your registers that you might need to persist information from there. But yeah, the sort of out-of-order eviction situation doesn't happen in that scenario. And I'm going to talk about systems in which we do. Can you
just give us a hint what a write-through cache is for those?
Yeah, the idea being that whenever you write something to cache, it immediately persists. It doesn't wait. There's downsides of that, which is usually it's less efficient. Okay. All right. So we're going to discuss, how to handle these sort of out-of-order evictions that usually happen in these caches. Okay. So how can we handle it? Yeah.
So if you crash, and say you were in the middle of, you like in your first example, you'd written 1 and 2, but not 3. But do you know that when you crash, you also lose your, where the program was, right? Like, do you know that's? Yeah. It's not quite the same as just being lock-free, right?
Right. So that's a good point. So with lock freedom, the nice thing is that you don't have to continue an operation. You're allowed to pause it and never go back to it with lock freedom. So you could technically say, well, I don't know what I was in the middle of doing. I'm just going to start fresh, right? So that is something allowable. If you do want to continue your operation from where you were, you have to persist more information. And there are several works that deal with just how to persist that sort of program counter type information to be able to continue from where you were. We actually had a paper about that too, but I'm not going to discuss it here. So for now, I'm going to assume that all we care about is sort of not continuing the same operations you were doing, but just having a memory state from which you can start new operations. Okay. But basically, it is a problem that you need to handle, but it's solvable, is the general takeaway. Okay, so what can we do from a programming or like algorithm design perspective to control these out of order evictions? We can insert explicit flushing, sort of tell the cache which elements to flush and when. Okay, we can do that. Right, so there are these flush instructions that tell the cache, well, I want you to now evict this first memory location onto the main memory. Okay. The thing is, just a flush instruction generally doesn't wait for this eviction to complete, right? So it's possible that I told it to flush 1, then flush 2, then flush 3. Maybe it completed 1, was in the middle of 2, and I don't actually know whether it terminated. It's also possible that I told it to flush all 3 of them, and it did 3 first before 2. Also quite a possible scenario. So to ensure that I've waited and I have the guarantee that whatever I flushed has actually made it to main memory, I can execute a fence instruction. Okay, and that's where I kind of block until I know that the flush completed. Okay. The fence instructions are what is expensive, but in this talk, I'm not gonna differentiate between flushes and fences. Okay, I'm just gonna say, whenever I say flush, I'm assuming I'm doing a flush and immediately a fence. Now, there are algorithms and situations where you could optimize some of that, so you could flush a bunch of things, and then at the end, sort of before you really need them to happen, you fence and you wait for all of them to happen. In this talk, everything that I will show will actually require fences immediately after flushes. So I'll just say flush, I mean flush, and wait for it to complete. Okay. All right. So we have this tool. We can tell the cache to flush a particular item and sort of get the guarantee that that item has reached main memory. So how do we use this? The problem is that we don't want to use a lot of flushes because they make sort of, if you flush all the time, you get rid of the advantage that a cache gives you, right? Because a cache is much faster than main memory, but if you wait for everything to be written to main memory before you continue, it's almost like you didn't have a cache in the first place. You don't want that. So the question is, where do we need to put in these flushes? Okay, so we could sort of do a first take, see if that works. Let's flush after every time we update the memory. Okay, so, and I'll show sort of that this won't work. Let's imagine that we have some algorithm that inserts into a linked list. This is the head of the linked list, and I have 2 threads that want to insert some item into it. Their algorithm basically says, let me read the head of the linked list, write in, sort of allocate my new node and write in a pointer from the head to my new node. And then I'll flush my update. Okay, so we can look at what might happen. So it could be that thread 1 reads the end of the list, writes in its new pointer and its new allocation, and pauses before it flushes. And then we have another thread that does the same. It sort of comes in, reads the end of the list. This time it sees that this is the end of the list, writes a new pointer and a new node, and then flushes its own new node. Okay, so we could get to this situation where sort of because one thread paused in the middle and didn't flush its update, but another thread depended on it, we could have this sort of disconnected linked list, and we would lose not only P1's update under such a crash, but also we wouldn't know where P2 put its node because we don't have a pointer to it. Okay, so this obviously doesn't work. Basically what happened here is that P2 had a dependency on something that hadn't been flushed. Okay, so we know that at least some of the time we would have to, P2, to fix this, would have had to flush P1's node itself, right? It can't sort of depend on P1 to do it for it. Okay, so that's sort of the situation. We don't want to flush everywhere, but we know that just flushing my updates is not going to be enough. There have been a lot of works in this area. There was actually one of the first works that dealt with it said, well, I can prove that if you do flush absolutely every read and every update, so after every single instruction, you execute a flush on that memory location, then you will preserve correctness in persistent memory. Okay, so there was this work that did that. It's very general. You can apply it for anything, but it ends up being very slow, right? You get to the situation where you flush absolutely everything, and it's almost like you don't have a cache to begin with. There have also been quite a few works that said, okay, well, let me take a specific data structure and sort of understand where the dependencies are really important in that data structure and flush only where necessary. Okay, so there were a few works that did that, but that ends up being sort of very work intensive. Okay, the solutions that they came up with were quite efficient. They ended up having significantly fewer flushes than just flush everywhere. But it's a lot of work. Sort of every data structure is its own paper. Okay. So what we would like is sort of to achieve the best of both worlds. We want it to be really easy to use in general, and we want it to be fast. Okay. So this is what I'm going to talk about. I'm going to show you two parts to this. The first is how to choose which instructions, which memory locations do not need to be flushed at all. And then afterwards, I'll talk about once you know which instructions you do want to flush, how to make sure that they're flushed less often. Because what can happen, and I'll show you how that can happen, is that several threads end up trying to flush the same location, right? So even in our previous example, it could be that P2 decides, okay, I'm going to flush P1's update because I don't know if it's been flushed, but P1 is also going to flush it. So now we've waited for two fences when we really didn't have to. Okay, so first part, we'll talk about sort of discovering which instructions need to be flushed, and then the second part, how to make sure that each instruction is flushed as few times as possible. Okay. Okay. So in the first part, I'm going to present our own work. It's called NV Traverse. NV for like the non-volatile memory, and traverse because we're going to discuss specifically data structures that have traversal phases in them. And it's going to be basically an efficient general construction for persistence. By efficient general construction, efficient means we're not going to flush every instruction, and general means it's going to apply to a large class of data structures. It's not going to apply to absolutely everything. Okay. Okay. And so I'll very briefly show you sort of the high-level idea, and then I'll show you like one experimental result, and then we'll move on to the next section because I don't want to take up too much time. The idea is that if we have sort of pointer-based data structures, we often start with a traversal before we get to like the place we want to modify. So if I have a tree, I want to insert 6, I sort of traverse down the tree first, and then I discover the place I want to make my modification. Okay. Now in this traversal, if, say, this node was like 8 instead of 7, I really don't care. It didn't affect my traverse at all, right? So I don't actually have to persist everything I see because the specific values that I read don't matter. Okay. So that's the high level, sort of the intuition for what we did with NV Traverse. The idea being, let's traverse without doing any flushes, and when we get to the key place we modify, that's when we'll start persisting everything. Okay. We also kind of gave it a funny name where we said, if you think of the traversal as the journey and the destination is the place you modify, in persistent data structures, the destination actually does matter more than the journey. So that was sort of the funny title of our paper. Okay, so the idea is as follows. We're going to define what a traversal data structure is. And basically, it's a data structure that follows some traversal, like a tree, like a linked list, and sort of doesn't heavily depend on that traversal, and we define that in the paper. Once you give me a traversal data structure that satisfies lock freedom, I can automatically convert it into a persistent data structure. And this conversion is fairly efficient. It doesn't flush everywhere, and we show that it's pretty good. So that's our contribution. However, many lock-free data structures are like almost traversal data structures, but they don't quite fit our definition, so you might need to modify them a little bit, and we don't give an automatic way to do that. But for most data structures we looked at, the modification was very simple. Okay, the idea of how to define a traversal data structure was basically, let's make sure that we know exactly what passes between a traversal and sort of the place where you modify things at the end. Okay, so we define the traversal phase as a function that basically outputs just a very small amount of information. Okay, and the intuition being that the traversal does some very local computation with the information that it sees. It sort of uses maybe just the information that it saw on the current node, maybe one before it, and that's all it uses to do the traversal. And at the very end, when it reaches its destination, it outputs the last, I think it was 2 nodes that it saw. Okay, so it only ever remembers sort of the last 2 values it saw. It forgets everything else, and it outputs that information at the end. Okay, so we can kind of have the guarantee that we don't need any other information once we get to the modification. And then that's all that we flush. Okay, so basically once you give me a traversal data structure, what I'm going to do is I'm going to flush the traversal output and then flush everything that I do in the critical section or the modification phase. And once you have that, we have a guarantee that you'll have a correct persistent data structure. All right, so very quickly, experimental results. We compared against, so the orange bars are the hand-tuned versions, and the other ones are all sort of general constructions. Here, higher is better, so you can see that the hand-tuned versions are still more efficient than traversal data structures. And here, what we're seeing is growing list size or growing traversal size. And so basically, you can see that when the list is fairly short, we're not very competitive with hand-tuned version because we don't gain that much for no flushes on the traversal. But as the traversal grows, we actually become very competitive with the hand-tuned versions. Right? And in any case, even in the short traversal cases, we're still better than the general constructions that existed at the time. So that's sort of the takeaway here. Okay.
Can you just say one sentence, like what were the hand-tuned ones who were better on the short ones? Or like...
Yeah, so the traversal, basically we assumed, we could show a fairly general class where if you remember like the last 2 elements in your traversal, and then you remember sort of you flush everything that you do, then you're good. The hand-tuned ones can say, well, I actually didn't need the last 2, I only needed the last 1, or I don't need to flush everything that I'm doing. It can really look at data structure details and flush less. Okay, so now I'll take a few more minutes to sort of tell you about one other work which said, okay, well now we know which instructions to flush, but we don't want to have several threads flush, all of them flushing the same place that is sort of redundant. Okay, so for that we had another paper. It was called FLIT, which was basically a general tool, or it was actually, we implemented it as a library that decreases redundant flushing. Okay, so again, so our goals is instead of talking about which instructions need to be flushed, we assume that we now know which ones need to be flushed, and we ask, well, who needs to flush them? Okay, which thread is going to flush them? Because so far, we've just assumed that every thread will take that responsibility and will have redundant flushing. Okay, so if we remember the example at the beginning of, we wanted to insert into a list, and we had sort of this inconsistency that happens where, we sort of showed that P2 would have to flush its read as well in order to be consistent. Well, again, that's the case only if P1 hasn't flushed it already itself, right? So now we want P1 to be able to leave an indication for P2 to see that, oh, hey, I actually already flushed this, so you don't have to. Okay, that's the idea. And so how do we do this? There was work from 2018 that actually had an idea for this. It said, well, we're going to take a bit in each word, and we're going to basically use it as a flag for whether this needs flushing or not. So whenever we modify that word, we set that bit. So the flag says now, okay, this word has been modified but not flushed. Then we persist it, we flush it, and after that we come back to the word and we do another compare and swap to unset the bit. Okay, and then if you see that the flag is off, you don't have to flush it. Okay, The disadvantage, though, is that you do need a bit per word. In some algorithms, that's perfectly fine. In others, they actually optimize for all the bits in the word, and you can't take away a bit from the word. They also needed to use compare and swap instructions, right? And that can also limit the generality in some cases. Okay, and this is just an example. You flush, you turn off the bit, you're done. Okay, so now our idea said, okay, well, let's basically take this flag idea, but instead of just using one bit, we're going to have a counter. Okay. Okay. The counter.
Question back on that. So it's it's a flush then a fence. So that's how you know you can set the bit. The flush has actually been done.
Yeah.
It's not enough to just say, oh, I issued the flush.
No, you flush and fence. So in this talk, I always assume I flush and immediately fence. Yeah. Okay. So now we're going to have a counter, basically a thread that modifies the word will increment and then come back and decrement after it's persisted the location. And the nice thing about this now is that we can physically separate the counter from the word that's being persisted, right? We can put it somewhere completely different. We can put it next to it, but now the word doesn't have to give up one of its bits. Okay, and and basically, if you have an operation that you know from like general constructions or whatever, from NV traverse or whatever other general construction, that it doesn't need persisting, then you just ignore the counter completely, right? You don't increment it, you don't decrement it, that's it. Okay, so now if you want to persist something, you do the persistence store. Basically, you increment your counter, you execute your modification, then you flush, and then you decrement your counter. And then when you read, basically you check if the counter is higher than 0, then you persist it, and otherwise you don't. Okay. So that's the idea, basically counters instead of the flag. Okay. But the nice thing about being able to physically separate these counters from the words that they are sort of designated for is that now you can sort of play with this quite a bit, right? You can say, well, I don't want to have a counter per word. Maybe I want to group a bunch of words together, and whenever the counter is non-zero, this word will be flushed. Maybe it'll be flushed unnecessarily because the counter was actually non-zero because of another word that maps to the same counter, but that's okay, right? Extra flushing doesn't hurt our correctness. It just hurts our efficiency, but we can sort of play with that. Okay, so basically the place where we put these counters and also the number of memory locations that map to the same counter will affect our efficiency in the sort of at the high level. We sort of looked at two main options. One is to leave the counter sort of next to the word, either like two words right next to each other, or have, say, a counter per cache line where the counter sits on the cache line, or maybe you want a counter per node where you put the counter inside the node. But you could also sort of have a completely different approach where you put a hash table with all the counters in there, and then every memory location hashes into the hash table and just increments the counter that's there. Okay, so you could sort of play with that. And then we did sort of an experimental evaluation where we compared our adjacent approach to the link and persist was the approach that just had a bit as a flag, and then also to the hash table approach. And the blue bar is sort of plain without any of these optimizations. And we can see that you should have like a flag and or a counter. It's very helpful compared to the version that doesn't use any counter at all. And we can also show that the hash table approach was actually a little bit more efficient in all cases that we tested. So basically placing the counters in a different location and hashing to them, and then we played with the size of the hash table, which I'm not showing here. But basically having a hash table separate from the memory location itself was more efficient, and we ended up having fewer cache misses this way. Basically because if you have to come back and update a word that's right next to where you just updated, and you just flushed. Okay, so if you have the two places next to each other and you just flushed the word out of your cache, it's quite likely that you're gonna cache miss on the thing that's right next to it, right? If it's on the same cache line, you flush that cache line out of your cache, and so on. So the hash table approach was somewhat more efficient. We tested a few options there. But I think I'll end my talk here. So just some concluding thoughts. I sort of showed you a few approaches of how to implement persistent data structures more efficiently. Like I said at the beginning of the talk, NVRAM itself actually isn't supported by Intel anymore. There are other emerging technologies that can give you somewhat of a similar interface. So for example, CXL sort of allows you to access the memory of different nodes or different machines sort of in a transparent way. And that can give you the illusion of persistence because your memory might be stored in several places and the likelihood that all of them will crash is much smaller. And so you then end up having to do a lot of the same considerations that you have with persistent memory like NVRAM. I will say though that sort of the two works that I talked about, I think are interesting and of sort of independent interest, and their insights will come up for other memories as well. With NV-traverse, we really just studied the inherent dependencies that there are in these data structures, which I think is an important thing to understand. And with the FLIT, with the counters, really what we offered is sort of can be seen as a software solution to a hardware problem. Because if the hardware could just tell me which cache lines in my cache are dirty or not, I wouldn't need FLIT, right? So it's sort of something that I think might be possible to just do in hardware if we find that there are enough useful applications for I need to know whether my cache line is dirty or not, right? Yeah, and with that, I'll finish and take questions. Yeah.
Yeah, so this came up briefly. I think my initial question was, is there this monotonicity property about additional flushes where, and I think you mentioned that additional flushes, you guarantee like the problems you're considering don't affect correctness.
Yeah.
But is there a meaningful class of problems here where that's going to become a problem, where I have to worry about additional flushes from some adversary or other things in the cache evicting me before I anticipate?
So I mean, this whole model kind of assumes that you could imagine an adversary evicting things in the order that it wants, and you're adding flushes to sort of fight that, right? You're saying even if things have been evicted out of order according to some adversary, the order that I'm insisting on is going to guarantee correctness. That's sort of the name of the game. And if you add extra flushes on top of the order that you're insisting on, then it doesn't hurt, right? I mean, it hurts efficiency, but not correctness. Yeah. Mm-hmm.
So I think the example you gave for NV-traverse with the tree, right? You're doing a series of reads followed by a write or two writes, maybe, right?
Yeah.
So was that the structure that you look for, or could there, do you have a way to automate it even if there are reads and writes?
Yeah. So no. So with the NV-traverse data structures, we need the traversal to not make any modifications. We don't handle modifications. Basically, we assume that any modification is probably an important one, and you will have to persist it. And in the NV-traverse definition, we don't allow any modifications in traversals. You could maybe extend it to that, but then you would have to argue that a modification that I made was actually not important in some way, and then you would have to get into the nitty-gritty of like, what data structure are you building and why isn't it important? So like as a general construction, without opening the black box, we didn't touch that.
I see. It's like doing a balanced binary tree.
Right. You could say, okay, well maybe the balancing isn't important, but yeah, we didn't get into that. You would have to sort of argue about why this particular thing wouldn't matter. Right. Yeah. Yeah.
So one thing I'm missing is you talked about counters and stuff per word, but the flushing is a cache line granularity. So why wouldn't the counters be a cache line thing as well?
Right. So you could do cache line granularity.
You can't flush a sub cache line. It's like all or nothing. You're getting
Right. I think so. So in the original sort of in the original bit idea instead of a counter, they needed it to be in the same word because they needed to atomically change it with the cast. So if they're modifying the word, they want to atomically also set the flag.
Okay.
Okay, so that's why they needed sort of the flag to be there. For us, we don't, once we separate the atomicity part of it, then yeah, there's no reason to do it per word. You might as well do it per cache line.
Okay.
Yeah. Yeah.
So you probably don't, it's probably a question you're not going to have an answer to, but I just wanted to make this point that, if I understand, so you're saying that this persistent memory it's not being manufactured anymore, right? So,
Yeah.
but you have solved a problem on it, right? So
Yeah.
if someone comes around in 3 years and decides they're going to just make a different persistent, memory,
Yeah.
you really like them to know about,
Right.
your work or the other.
Yeah.
Is there any, is there an ecosystem? I know when Martin was asked this question, he went off on a rant, right? So is there, is there like an ecosystem where, do the people who design this know about this work?
Yeah, I mean, that's a good question. And I think, kind of like the rant Martin went on, I think, there's sort of always this gap between, the work that academia does and the work that industry does. And I can't give you a guarantee that everyone who works on these memories in industry is aware of the literature and body of work that exists for NVRAM and whether it would apply. I would hope that they're at least aware that there exists such a body of work and that and they know that they're doing something similar to NVRAM. So when they come up with a new memory, I would hope that at least, they would say, hey, let's find the people who worked on it then and they can tell us if it's relevant. I think just like a vague awareness of this exists, I think we have that. I can't tell you how specific the
So it may
the
work out better
knowledge
than
is.
that, right? With these
Yeah.
chatbots, they may, the architect person may have a general question and they may find her work, the chatbot, and report it to them, right?
Right. If it doesn't
That'd be nice,
hallucinate,
right?
yeah, no.
So NVRAM does not exist because it was economically not viable, or it was replaced by the JAX?
Yeah, it was. I think Intel decided it's not gonna spend more time and money on it. I think that was the reason. It's not that it didn't work. It's just that they put in a lot of effort into it, and there were a lot of sort of issues that came up when this existed. I've only talked about a few of them, right? And so I think because there were so many sort of issues around it, they said, you know what, we're tired of this, and they stopped supporting it. So, yeah.
I mean, I think about this last thing about FLIT is a software solution to a hardware problem. And if the hardware are gonna have to keep track and be able to tell you if something is persistent, for the L3 cache, that's actually a large amount of information and it's slow to access that cache. It's already, multiple from
Yeah.
I actually imagine FLIT might be the hardware the thing
Maybe.
they would do in
I mean,
hardware.
maybe. Yeah. If they could implement basic. I mean, it's not very far from what you would have to do in hardware. You would have to keep track of this information, right? So we're doing it in software. I think it's not outrageous to think they would be a hardware mechanism would be able to do something like this. It's not super difficult, but right now, yeah, it doesn't do that. So.
All right, let's thank Naama again. In principle, we should have coffee out there, and in case you're here a little late, this is it, the docs.
Here's the rest of the day to collaborate.
Yes.